In this lesson, students will use the scale factor to determine areas of similar figures. So we're going to start by looking at these two similar triangles. They each have a base and a height dimension. And we will start with the linear scale factor. So I want to denote this language, the linear scale factor, because now we have to delineate between a linear scale factor and an area scale factor. So the linear scale factor, that's going to be the scale factor for corresponding linear measurements. That would be sides, perimeter, any other kind of corresponding dimension, altitude, base, whatever, okay? So that's our linear scale factor. What we want to do here, though, is we want to find the areas of these two triangles. So the formula for area is 1/2 the base times the height. And if I find the area of the larger triangle, it's 1/2, 8 times 4. So that's going to be 16. That's the first guy. The area of the second one is 1/2, 6 times 3, and that's going to be 9. Okay, so when you look at those two areas, the scale factor isn't the same as the linear scale factor. So let's look at this. The linear scale factor, let's do that, which we've been calling R, is 6/8, which reduces down to 3/4. Actually, I could have just said 3/4 because that's what the altitudes are. Okay. The area scale factor, so the scale factor for area, whoops, if I can spell it right, okay, that's going to be the ratio of 9/16. That is not the same as 3/4. But there is a relationship between the two. Okay, if I look at 3/4 and I square it, that's going to give me 9/16. So that is going to be the relationship. The area scale factor is not the same as the linear scale factor. So that's what you have to remember. The ratio of areas, the area scale factor, is not the same as the linear scale factor. So this leads us to our similar polygon area theorem. So here it is. If two polygons are similar, then the ratio of their areas is equal to the ratio of the squared lengths of their corresponding sides. So it's not the same ratio, you have to square it. So another way to write this is the ratio of the areas is equal to the square of the linear scale factor. So you find the regular scale factor and you square the top and you square the bottom, and that's the scale factor for the areas. So let's look at some examples. Here's the first one. Two polygons are similar, and a pair of corresponding sides measure 12 and 9. So I don't even know what the polygons look like, but I know a pair of corresponding sides measure 12 and 9. And the area of the larger polygon is 72. We want to find the area of the smaller one. So this is where you have to use this concept because you don't have enough information to calculate it otherwise. I have bigger and smaller, or larger and smaller, and here the area of the larger is 72. So we can write some things down. We have a larger side is 12, larger area is 72. We have a smaller side, that's 9, and we don't know what the smaller area is. We cannot just set up a proportion. We have to we can set up a proportion, but we have to square the sides to do it, okay? So if x is the smaller area and 72 is the larger area, then that's going to be equal to the smaller side squared divided by the larger side squared. So that's x over 72 is equal to 81 over 144. 144x is equal to 5832. And, well, let me move it up. There it goes. X is equal to 40.5. Okay? So that makes use of the first way of saying this statement. The ratio of the areas is equal to squaring the sides and taking their ratio. Okay? An equivalent expression would have been this. X over 72 is equal to 9 over 12, the whole thing squared. Because when you're squaring that entire thing, you're squaring the numerator, you're squaring the denominator, and it looks just like that. Okay, here we have rectangles A and B. They are similar to each other. For A, I have 2 side lengths. For B, the only thing I know is the perimeter is 16. So the first thing we want to do is find the linear scale factor. In order to do that, I need some corresponding measurements. I don't really have that yet. I have only perimeter over here, but I have enough information over here to find the perimeter of rectangle A. So you're going to find the perimeter, and perimeter is a linear dimension. You can use that for a scale factor because it's just the sum of other linear dimensions. So the perimeter of A is going to be 2 times 10 plus 2 times 6. So that's 20 plus 12, that's 32. So the scale factor is going to be 16 over 32, so that's 1/2. That's part A. For part B, we're going to find the ratio of areas. So all I have to do is take the linear scale factor and square it to find the ratio of areas. So that's going to be 1/2 squared. So 1 squared is 1, 2 squared is 4. So the ratio of areas is 1 to 4. And then finally, we want to find the area of rectangle B. Well, we can first find the area of rectangle A because I have those 2 dimensions. The area of A is going to be 6 times 10, so that's 60. To find the area of rectangle B, you can set up a proportion. AB over 60 is equal to 1 over 4 because that's the scale factor for areas. And when you cross multiply, you get 4AB is equal to 60. So the area of B is going to be 15. So that's how you use the little information you have and the concept of similarity to find the other things you need. Okay, these types of problems are really not complicated, so don't make them more difficult than what they are. Find the ratio of areas of 2 similar polygons when the ratio of corresponding sides is 3 to 7. There's your linear ratio. All you have to do is square both numbers. You don't even have to show any work. Okay, so the ratio of areas is going to be 9 to 49. That's it. Don't have to do anything else. And then finally, we can go in reverse. If I give you the ratio of areas, the ratio of areas of 2 similar triangles is 81 to 64. I want to find the linear scale factor. So I just take the square root of both of those. The square root of 81 is 9. The square root of 64 is 8. So the ratio of sides is going to be 9 to 8. And that is a basic introduction to using linear and area ratios.